just mentioned about the infinite number of trials. I don't want to ignore that, and I designed this to answer that question because it always comes up, and I love the fact that it always comes up. I put blue, WLOG, that means without loss of generality. That means we could have easily done it with the yellow dice, or the red, or the green, or the, what color did I forget? Orange, thank you. But I just happened to do blue first because it was sitting down in front of me and I said, let's do the blue. You can easily do it 4 other spreadsheets with the other colors. Here's the average and the standard deviation of the blue distribution. Who had blue? So these numbers agree with what you guys had, yes? 8.16 repeating and then 2.65-ish, rounded off. That's what the dice look like. This is called a net. If you blow the dice out, that's what will be on those dice. You can do this with any of your dice and figure out how goofy they are. Okay? Now, the first thing I did was I created a random number simulation, which I'll shrink down so you can actually see. Now, those of you who didn't have the blue distribution, or the blue dice, won't recognize this curve. But that is the curve that matched the blue distribution right there, isn't it? That's it. Now, that's the one you guys found, right? You guys found that distribution by turning the dice over and counting every single possibility. That's not what Excel did, though. Excel doesn't know how to count. Well, I shouldn't say that. That's all Excel does is count. But it doesn't know how to turn dice around. What I did was, I put the original distribution over here, and I randomly sampled using the random integer command, and I had Excel rolling. I think it's 10,000 different dice over here. So every time I press F9, it's actually rolling the dice again and summing up the results that it gets. So in other words, it's doing a census of the dice just like you did. Yours is more precise. It's more efficient because it's a computer. That's why we invented computers, was to be efficient. Think about it. You're more precise. Notice how it's wobbling. Every time I press F9, it's wobbling because it's not getting exact. But you see what those things are leveling off to? You're leveling off almost exactly to the distribution that the population has. And you see I'm a bastard. I changed the left axis to a probability axis instead of a frequency axis. So right now, it's saying that there's about a 20% chance of rolling an 11, just shy of a 20% chance. I'm a bastard because there were 7 out of 36 outcomes that are 11. 7 divided by 36 is approximately 20%, a little bit shy. See, just be a bastard. Just pay attention. Okay. And the reason I did that was I didn't want the number of trials to affect the axis. So I kept it as a percentage. See how some of you guys had 75 rolls, some of you guys had 50 rolls, some of your curves were much taller. Richie, you inadvertently did it when you typed 174 and it went through the roof and all the curves went yeah. I wanted to avoid that, so I went to a ratio instead of raw counts. Now, see if this looks familiar. What's the first thing you notice about that curve?
Perfect, almost perfect.
It's almost a perfect bell shape. Now wait a minute, this is the experiment you guys just did. This is it, sample of size 4. This is Excel, rolling the dice 4 times and then averaging the result. Roll the dice 4 times, average the result. Roll the dice 4 times, average the result. 4 times, average the result. It's doing it like 1,000 times though. If you scroll down, you'll see how many times I have Excel doing it. And that's why the bell curve is so much more fleshed out, because it's doing it. I think it's 1,000 trials. Yep, 1,000 trials, yes? So what you're seeing up here is the result of those 1,000. Do you notice also how I broke these up? They're not by ones anymore. It's not 7 to 8, 8 to 9, 9 to 10. It's 7 to 7.5, 7.5 to 8, 8 to 8.5. So you're getting a little more fill out of the curve there too, so that red will be taken care of in this case. More on that momentarily. So every time I press F9, Excel is rolling the dice, 1,000 more trials, 4,000 more times, and graphing. Can you find out, can you see where the average is? Remember where mu was? Mu was about 8.2. Where's the average, friends?
Right about that.
Right about where?
8.2.
Right. But where is it described in the location of the curve? Where is the average of 8.2?
8.
Most often in the biggest bar. Ha! Why are we happy about this?
We're supposed to be.
Because it's supposed to be. Because roughly 16% of the time, which is the mode, roughly 16% of the time, the average is in the bar where it's supposed to be. But then what do we say? Because we're somewhat pessimistic about that. 16% of the time, we're right where we're supposed to be.
The rest.
To which you counter 84% of the time you suck. Because the other 84% of the time you're somewhere else, yes?
But not, I mean, but you're not way over here.
Oh, good.
You know what I mean? You're not 84% of the time. You're not at 12 or whatever.
84% of the time you're not getting. Notice nobody's over here 11.5 to 12, or down here at Snake Eyes.
You're just shy on one side or.
Okay, but what if I'm down? I mean, what if I'm down here or down here? That kind of sucks, doesn't it? I love what you just said, Lauren. Thank you, by the way. 84% of the time you're off the average, but you might only be off by a half, which might be livable. Which might be livable. Good. Any idea how we could make this more precise? Right now, what we have is something called accuracy. We have accuracy. It's kind of like we're shooting for a target, and on average, we're hitting the bullseye, but that might mean, it's still a statistical joke. 3 statisticians go hunting in the woods. You ever heard this one? You probably haven't, because it's terrible. 3 statisticians go hunting in the woods. First statistician jumps up with a shotgun, shoots 5 feet to the bear's left. Second statistician jumps up, shoots the gun 5 feet to the bear's right. Third statistician jumps up and says,
I got it.
"We got him!"
We got it.
Because on average, we got it. But it's why, right? First hunter, second hunter, on average, we got them. Stick your head in the oven, feet in the fridge, on average, you feel fine, right? But the problem is that an average sometimes is too wildly varied, which means we have accuracy, but we're lacking what's called precision. How can we make precision better, do you think?
Center bar.
That would be nice if we could legally make that bar higher. Now, how could we do that? Go back to what Lauren said earlier about the 11 disappearing. Remember what you said about the 11 disappearing, the outliers disappearing? Sarah, what are you thinking right now? Go.
Narrow.
How can we do that mathematically, do you think?
Change our categories.
How?
Make them a wider.
Oh, love this. So the idea was, the reason 11 disappeared on the yellow graph was because it was too hard to average an 11. You see 11 1 in 36 times, but it's too hard to average an 11. Snake Eyes vanished over here. Blue curve. How many ways could you get Snake Eyes? Was it 2? Or 1?
No, 1.
It was 1. So 1 in 36, right? 1 in 36. So Snake Eyes is gone. You're not going to see an average of Snake Eyes.
No, we saw it show up. But
You saw it show up, but not an average. You have to get Snake Eyes 4 times in a row, in which case you go, I'm not going to Vegas anymore.
Yeah.
I would like to see these other outlier things disappear. Well, the only way to make them disappear is to do what? Make it harder to get them. So how are we going to make it harder to get them legitimately?
More.
Exactly. Here's where you have to think back to your couple last projects. Max and the pumpkin seeds, right? Why do you plant so many pumpkin seeds? To guarantee at least one of them germinates. Because the chance of all of them not germinating shrinks off to infinity as sample size goes larger. So let's go up to a sample size of 9. I would have never asked you to do this manually. Watch why. Now I'm going to have Excel do 1,000 trials, but now you've got 9 rolls that you're averaging instead. You see that? There's 9 different rolls instead of 4. 9 across here, that's the average of those 9. 9, boom. Notice what you're seeing up here, friends. What are you seeing? You're seeing what curve? What curve are you looking at right here? I'll make it dance.
Now steeper bill.
What are you seeing right here, friends?
A tighter bill.
It's a bell curve, but it's a tighter bell curve. Over here, when the sample size was 4, these little guys over here, you're seeing them pop up every once in a while, aren't you? There's a 3, there's a 3.5, there's a 4, a 4.5. When we go to 9, all of a sudden, look, these guys down here are gone, and this guy is very rare. Why are they disappearing? Why are the ends disappearing? Because it's too hard to get that. It's too hard to average 4 when 4 is rare in the population. It's like saying a rooster is 10% likely. This is going and buying 9 birds and getting 9 roosters. Sure, it can happen, just not very often. What are you seeing happen more often?
Less of the
roosters, but also we're also getting less of the extremes on this side, aren't we? So if we're getting less on this and less on this, what are we getting more of?
average.
Average. We're getting more of average. There has to be 100% area under the curve, right? If we're losing a tail and losing a tail, where does that lost area have to go? It's got to compress to the middle. And notice the highest bars are now above 20%. They were under 20%. They were at 16. Now they're popping to 20. How can we make it even better?
More
Increase
trials.
your sample. Let's go to 16. Here's 16.
Oh, wow.
Here's 16. Oh. We just answered this question, why the bar containing mu is getting taller. Notice it's up above 25% now. It's up above 25%. Here's a fun question. What's bigger? The standard deviation of that curve or the standard deviation of the entire population? Which one is larger numerically? So you guys already calculated the standard deviation of the entire population. It's 2.6, I think it was, 2.65. We'll call it 2.5 just to make life easy, 2.5. What's bigger, 2.5 or the standard deviation of that?
2.5.
2.5 is bigger. Why? Population. Why? What's the standard deviation of this?
Less.
Let's approximate. Since it's a bell curve, can we approximate what the standard deviations are?
Sure.
How can we do it? Hands. Tell me what. Give me more.
Five middle.
Middle.
95%.
What am I doing?
Spread.
Spread them till they're at. Tell me where to stop.
Oh,
Stop. Okay. 7 to 9.5. That's 2.5, isn't it? Well, hell, that's 2 standard deviations, which is as big as the standard deviation of the population. So clearly, S is smaller, isn't it? Because that, if you think about it, that 2.5 is 4 S's, right? Mu plus S minus S plus S minus S. There's 4 S's over that 2.5, which means S is exactly 1/4 as big as the populations. Does that make sense? You guys buying that? Let's look back at your curve, just to make sure we can convince ourselves of this. Here's your data, right? Where would 95% be for you guys? Tell me where to stop. Was that a stop or was that a sneeze? Somebody say stop. Stop? Okay. So 6 to 10.5, that's what, 4.5? 4.5-ish. 4.5. Cut that in half itself, so that's 2.25, which is essentially the same as the population standard deviation, but that's 2 S's, isn't it? It's up and down to get 2.5, so that's about half. So this one's S is about half the population standard deviation. This one's S is about 1/4, so clearly S is smaller than the population. Now, that's the mathematics. Why should it be getting smaller?
Because instead of taking, you're doing 4-year-olds in 1,000 trials, now you're doing 16-year-olds in 1,000 trials, so you're making it bigger.
Our estimate is getting more and more, it's the same accuracy, it's getting more precise. Precision means lower variation. That's the whole definition of precision, right? It's lower variation. How do we get even lower variation? Bigger samples. Bigger samples, 25. Holy crap. There's your bell curve. Look what's not showing up anymore. You're not getting 4s and 5s and 6s. You're getting some 6.5s. Can we do better? 100.
Uh-oh.
Now look, 60%. 60% or more are landing in the 8 to 8.5. Now some of you are going to say, that's not a bell curve.
Getting a little away from it a little bit.
That's the exact same thing you were just looking at. You see what I did to the axis to make it look like that? I broke the axis down by tenths instead of by halves. That's the axis by halves, right? 8 to 8.5, 8.5 to 9, 9 to 9.5. And I knew you guys weren't going to like that. I knew you weren't going to like that. Although, I like looking at it like this. Your average is 8.2, right? Which means it's not actually in the middle of this. It's a little bit to the left side of this. And that makes sense. This bar is a little fatter than that one, so it's pulling it this way a little bit. But I knew you wouldn't like that. You wouldn't call that a bell curve. So I said, okay, let's break it down. Notice the axis. This one goes down to 2. New axis goes only down to 7. And look, if you think about it, that curve looks exactly the same as that curve, doesn't it? But look at the axis. It only stretches from 7 up to 9.5. You guys buying this? What's the standard deviation here, shall we? Shall we? Shall we? Stop me.
Yeah.
Right there? 7.8 to 8.9. 1.2? Is that right? 7.8 to 8.9? 1.2, yeah? Is that 7.8 to 8.1? Oh, 1.1. Jesus, yeah, 1.1. Thank you. Adding, not my strong suit. 1.1. So that's 4 S's, correct? That's 4 S's. So 1.1 cut in half is 0.55.
Yeah.
I think 0.55. Cut that in half, it's about 0.25. It's about 1/4. 0.25. Your original was 2.5, wasn't it? It's almost a tenth. So S keeps going down as our sample sizes keep going up. Coincidence? Hell no! Why is it shrinking down? You guys already know why it's shrinking down. Because we're getting more precise, because it's getting too hard to get that far away from average. Remember what average means, it's the balance point of the distribution. It's where everything balances. So even though the mode might be off the average is where the distribution tries to balance to. Outliers are not. So these curves, these bell curves, are not coincidental. They happen because they have to happen. Because the distribution is trying to find its average on average. Now we're not going to do the next bit in 5 minutes. Let's call it a day right now. We'll come back and recap on Thursday. It'll be probably a pretty short day Thursday. Pretty short day. And we can understand what the hell's going on right now. You're getting close. You could probably knock a few of the questions off of the exam now. I'm betting after what you saw today. If you look at the exam, you're shaking your heads like, yeah, I've seen it now. If not, don't worry. After Thursday, you will.
Yeah, we did that all.
If you did the quiz, let's turn it in right here.
You don't think we're supposed to?
And we'll catch you again on Thursday, yes? Go get them. Week 10, baby. Last in-class quiz.